In this video, we're going to talk about measuring angles in radians rather than degrees. But before we can really define what a radian is, we need to talk about the concept of arc length. So we'll usually use the symbol S to represent arc length, and in this class we're really going to be interested in looking at the length of an arc along a circle. So some language that we'll use here is when we refer to an arc length, we'll often refer to it as the arc subtended by a particular angle theta. Okay, so here, for example, notice that theta, I don't know, maybe I think it'd be fair to say that that's somewhere around 60 degrees. And let's just say for a second that the radius is equal to 4 inches. So the kind of language we'd use here is that we would say S is the arc along a circle of radius 4 inches subtended by, which really means drawn out by, the angle 60 degrees. Okay. So let's work with this idea of arc length a little bit. So I've got two circles here, and these two circles have different radii. So the radius of this smaller circle is 2, and the other one has a radius of 3. And so what I want us to do in part A is recalling, first of all, that the circumference of a circle is given by 2 pi times the radius. Find the arc length shown if theta is 45 degrees. So if in fact this is 45 degrees, as it kind of looks like it may be. Just real quick here, this value pi, remember it's approximately 3.14. You've probably used that many times in your past. Let's not do any approximating here. Let's just leave pi as the symbol because it's not exactly equal to 3.14. All right, so let's take this one at a time. Let's start with the circle of radius 2. Now, if theta is 45 degrees, let's remember what we talked about in the last video, where we said that 45 degrees, remember, was associated with 1/8 of the circle, right? So what we could say is that S, the arc length, is 1/8 of the circumference. So what I could do here is just say, well, then if I want to find the arc length here, I could just take 1/8 of the circumference, but we know the circumference is 2 pi r, right? And since our radius here is 2, I put 2 in for r. But that just gives me 4 pi, right? 2 times 2 is 4 over 8, which is just going to give me pi over 2. And I can apply the same principle to the circle of radius 3. So again, 45 degrees is still 1/8 of the circle, so I can say let's take 1/8 of the circumference. But this time the circumference is calculated by 2 times pi times 3, since 3 is my radius. So that becomes 6 pi over 8, which is 3 pi over 4. All right, so we've answered the question in part A. Right? We've found the arc lengths shown in the two pictures above. But now what part B wants me to do is to divide each arc length by the radius of its circle. So in other words, let's compute S divided by r. Okay, so if we do this for r equals 2, we saw that the arc length was pi over 2 for that circle and for that arc, and then dividing it by 2. Of course, that's not simplified, so let's do a little bit better job. Dividing by 2 is the same as multiplying by its reciprocal, so this is just pi over 4. And I can do the same thing with r equals 3. For the circle of radius 3, we found that the arc length was 3 pi over 4, and the radius was 3. So 3 pi over 4, and I suppose, let me show a little more detail this time. I'm dividing by 3 over 1, right, when I divide by 3, so that turns into 3 pi over 4 times 1/3. And I get a little bit of nice cancellation there, and I end up with pi over 4, right? So what I see here is that I got two different answers for the arc lengths, as I should, because this is a much bigger circle when the radius is 3 than when the radius is 2. But when I take s divided by r, I get the same answer for both circles. So let's think about what was the thing that was the same between the two circles, right? The radii were different, the arc lengths were different, but the angles were the same. So it turns out that this quantity, s over r, is another way of capturing the idea of an angle. Okay, and this leads us to our definition of radians. So we define radian measure on a circle as being the ratio of the arc length along that circle divided by the radius of the circle. So it's this formula here, s divided by r. A lot of times you'll see me just write it like this: theta equals s over r, with the understanding that theta in this case is measured in radians. Now, a couple of things that are noteworthy. First of all, if the circle that we're measuring the angle on happens to have a radius of 1, we call this type of a circle a unit circle, then in the formula there, r is just 1. So in such cases, the radian measure of the angle and the arc length are exactly the same thing. We will be looking at unit circles quite a bit in this class, so that's why I note that here. And the one other thing to note is that both s and r are measured in the same units. So let's just say for a second that here's a circular arc, and I'm interested in what this angle might be. And let's just say that my radius here is 5 inches and my arc length is 2 inches. So if that were the case, following the formula, I would say this is 2 inches, being careful to include my units, divided by 5 inches. So it's interesting to note that the units there cancel. So since there are no units left after I cancel, we see that radian measure is actually a unitless measure. So while your math teachers are usually harping on you to, always include units with your answers, right? If your answer is in yards, make sure you put yards, that sort of thing. When you're asked for a radian measure of an angle, it's actually proper to leave the units off. And the one exception is that even though it's not a real unit, what some people will do is they'll go ahead and write RAD for radians. And that's not because radians are an actual unit. It's still unitless, but it helps the reader to remember that this angle is being measured in radians as opposed to degrees. And so you may want to use that at certain points during this class. That's fine, but it's also completely correct just to leave it completely unitless. So with our new definition of what it means to measure an angle, but now in radians, I like to do the same thing we did with degrees, which is to take a circle and note some special angles that are important for us to have memorized. So if you recall, the way we approached that with degrees is we started by saying there are 360 degrees in a circle, or 360 degrees in one full revolution, and so let's then break that up, take fractions of that 360 degrees, and those ended up being some of our special values. So let's make that same note here, right? That one revolution equals a full circle. And so if I go one revolution and I use my formula, arc length divided by radius, notice that the arc length is the full circumference, right? If you go one revolution around the circle. But circumference, we reminded ourselves in an earlier slide, is just 2 pi times the radius. And so notice what happens here is that the radii cancel, and you're left with just 2 pi. So with one revolution, theta in radians gives you 2 pi. So, again, let's start in standard position. So this will be 0. But I know if I go one revolution around this circle, that'll be 2 pi radians. All right, and then we, with the degrees, we noted that the black lines broke the circle into 4 pieces. So, I think we can do that here. So this time we'll take 2 pi divided by 4, which of course simplifies to pi over 2. So after a quarter, I'd get pi over 2. Plus another pi over 2 is 2 pi over 2, which is just pi. And then 2 pi over 2 plus pi over 2 is 3 pi over 2. All right, now let's do the same thing. Let's do that with the blue marks this time. So if we combine the blue marks and the black marks, it should be apparent that that would break the circle into 8 equal parts. So let's take 2 pi divided by 8, which simplifies to pi over 4. So this first blue marking here is at pi over 4. Pi over 4 plus pi over 4 is 2 pi over 4, which is pi over 2. 2 pi over 4 plus pi over 4 is 3 pi over 4. Plus a pi over 4 would be 4 pi over 4, which is pi. 4 pi over 4 plus pi over 4 is 5 pi over 4. And you get the picture pretty quick here. This is 7 pi over 4. And then we once again play the same game with the red lines combined with the black lines. They clearly break the circle up into 12 equal parts. So that's going to be 2 pi divided by 12, which simplifies to pi over 6. So this has got to be pi over 6. And then pi over 6 plus pi over 6 is 2 pi over 6. But 2 pi over 6 simplifies down to pi over 3. 2 pi over 6 plus pi over 6 is 3 pi over 6, which is pi over 2. 3 pi over 6 plus pi over 6 is 4 pi over 6, which is 2 pi over 3 when simplified. And then 4 pi over 6 plus pi over 6 is 5 pi over 6. And following the same pattern, we can get these other special radian values on the circle as well. So as was mentioned in the video where we worked with degrees, this is something you need to commit to memory. We're going to need to be able to recall where these particular values are on the circle quite readily. So make sure you work on that. All right, one example that we like to do here to finish up is to look at a similar problem to what we did with degrees when we talked about coterminal angles. So remember, two angles are coterminal if they terminate in the same spot on a circle, but they are different values. So let's take this negative 13 pi over 6. Now, coterminal angles with degrees, we found that we could get those just by adding or subtracting multiples of 360 degrees, right? Because that would always land you on the same spot on the circle. So now that we know that 360 degrees goes along with 2 pi radians, then if we're in radians, we should just be able to add and subtract copies of 2 pi. Now, instead of just jumping straight into adding 2 pi to this, a strategy that you might want to employ is, if you're not sure, go ahead and divide by the coefficient in front of the pi here, negative 13 divided by 6. And the reason for that is it'll give you a heads up as to whether adding 2 pi will do the job that we're wanting it to do, which is to give us a positive angle that is coterminal with this. So I can see that because negative 13 over 6 is negative 2.17, if I add 2 pi, that is not going to give me a positive angle value. So instead what I'll do is I'll add 4 pi, right? Because I want 2 copies of 2 pi. And that then will not only give me a coterminal angle, but it will give me one that is positive. So of course here I need common denominators. So this is 4 pi over 1. I think it's nice to grab a different color here. So we're just going to multiply by 6 on top and bottom. And so this is going to give me negative 13 pi over 6 plus 24 pi over 6, which gives me 11 pi over 6. And while the question didn't explicitly ask for it, based upon what we learned on the previous page, I know that this angle, if I'm on the circle here, it's not a very good circle I just made, but this angle is right about here. This is where the angle terminates on the circle because of the fact this is where 11 pi over 6 was on the circle on the previous page. So, excuse me, negative 13 pi over 6 must be in the same place there as 11 pi over 6 because they are coterminal.